Hello, everybody, once again. Hope we're all having a wonderful start to our week. This is starting our new section on section 3.1 where we're talking about the idea of the derivative. This is a very important idea in calculus. It's very foundational, and we're going to spend a lot of time with this. So let's just make sure that we have some familiarity with what we're talking about. I'm going to try and use the laser pointer. So the first thing I want to talk about is I want to talk about the idea of what we call a secant line. And this is a line that travels through 2 points. You give me a function f and a starting point and a stopping point, and I can find a line that travels through them using this as an equation for slope. Now, we use the letter m to represent the slope, and we also write SEC, that's standing for secant line. Now, this is somewhat related to the trigonometric term secant, but only very loosely. Really, you should just think of this as a different use case of the word secant. Now, notice this is the slope, because it's an m, from x equals a all the way to x equals b. And if you go down here on the left, you see I have my first point, I have my second point, and we connect those 2 points with a line. And in a certain way, you can think of this line in green as the average travel that this upper portion receives, right? You go up and to the right a little bit, and then you go down and to the right a little bit, and those overall is just kind of like, just traveling straight to the right. Now, we're going to change that idea. We want to talk about the ideas of the tangent line. Now, the tangent line looks very similar to the idea of a slope. It has a y2 minus y1 over x2 minus x1, that old idea for slope, but it's only using 1 point. And the reason we can do that is because if we let x equal a, x minus a term in the bottom, this is dividing by 0. Bad. So instead, what do? Well, anytime we wanted to divide by something that looked like 0, we said, okay, don't divide by 0, take the limit as it approaches 0. And right now, there's 2 ways of writing this. I want you to get kind of used to this second form right here with the h's. That's going to be very helpful going on. And you can think about h. H is an increment. It's how far away from the step we're taking. So we go from a to a plus h, and as h approaches 0, these 2 things are the same when h goes to 0. But we'll start at the beginning. We'll start using these kind of interchangeably, but ultimately I want to point out the second one is maybe a little bit more useful. Okay, looking over at the graph right here, we can see the line of the tangent line. And notice the tangent line, only 1 point, it kind of glances off the curve. And it really represents the slope of the function at a single point. We sometimes refer to this as the instantaneous rate of change, aka IROC. Now, some texts refer to this back secant line as an average rate of change, or AROC. But I will say it's less common to see. We're going to refer to this as instantaneous rate of change kind of a lot. Okay, so let's try it. Let's utilize this definition, and let's see if we can't come up with some of these slopes of tangent lines. And hopefully we'll also be able to take a look at some examples and kind of see why they are tangent lines. So here's what we need. We need to find a m sub tangent. First, you need to start off with a function. 2, you're going to need a point, which is just a starting location. So for the specific example coming from your homework, we're going to take a look at first a polynomial, 4x squared plus 2x, and we're going to take a look at the point p, negative 2, 12. And notice, the most important thing is that f of negative 2 is going to be 4 of negative 2 squared plus 2 times negative 2. This is going to be 4 times 4 plus 2 times 2 is going to be negative 4. It's going to be 16 plus negative 4, or 12. Notice this point is a true point. You don't usually have to verify these things, but I just always wanted to tell you this has to be a point on the curve. Now, we're going to go up, we're going to use our limit. So let's start off with the h definition. So this is going to be the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. Now the important question is what is a? A is our starting x value, which, in this case, we see as negative 2. So the next question becomes, we need to come up with what is f of a plus h. We need to know what that looks like. And we also need to know f of a. I'm going to start with the second one, just because it's a little bit easier. In fact, it was actually given to me at the beginning. I know f of a is 12. But the good question to ask is, what is f of a plus h? Whoops. I'm going to pull that up here. I'm just going to go to the side, and we're going to see if we can't answer this question. So, what is f of a plus h? We're just going to expand it as best we can. Reminder that a equals negative 2. So this is, according to our function, 4 times negative 2 plus h squared plus 2 times negative 2 plus h. Or 4 times what is negative 2 plus h squared. Remember, we use some foiling. We multiply everything by everything. We get 4 minus 2h minus another 2h plus h squared. Combine those two, 4 minus 4h plus h squared. Distribute out the 2. We get minus 4 plus 2h. Let me get rid of this. Once again, we'll distribute out. This is going to be 16 minus 16h plus 4h squared minus 4 plus 2h. Those two things combined, and those two things combine. And we can write this as 12 minus 14h plus 4h squared. That is our expression for f of a plus h. So, we have f of a plus h. We have f of a. Now, we're going to just plug it in. And what we're plugging it into is this definition over here. So this is the limit as h approaches 0 of f of a plus h minus f of a. So once again, this is the limit as h approaches 0. I'm going to use some brackets just to remind me. What is f of a plus h? We look over to the left-hand side. We found that it was 12 minus 14h plus 4h squared. what was f of a? It was 12. And we divide by an h, just to keep it inherited from the previous line. Okay, what cancels? 12 and 12. And here's my big tip for you. This always happens in that your constant term goes away. This is always, always, always going to happen. Okay? Now, this is the fun part. This is going back to our limit definition. Notice we are left with something that only involves h. And reminder, h is approaching 0, but it doesn't equal 0, which means I can divide this h from this h and one of those. So this becomes the limit as h approaches 0 of negative 14 plus 4h over 1. This is now continuous, so we can just plug in h equals 0. So this becomes negative 14 plus 4 times 0 over 1, or negative 14. So, what exactly is negative 14? It is the slope of the tangent line. And as a way of, more justifying this, I think it's always important to take a look at the graph. Okay? So, reminder, our original function was fx squared, 4x squared, plus 2x. We had the point, negative 2 comma 12. Let's zoom out a little bit. And you can see that point does actually appear on that graph. Now, we want to talk about the slope of the tangent line. So you can almost imagine it kind of this glancing line, this glancing blow, if you might think about it like that, as you're chopping something and it just slightly deflects off the curve. And it is a slope, y equals negative 14. Now, this green line has the same slope as the red line does through this point. But notice the green line is not in the right location. If we go back real quick, we know the tangent line is negative 14. We know the slope of the tangent line is negative 14. We should be able to write y equals m tangent times x plus b. And as a reminder, we know x, we know y, we know m tangent. Negative 12 equals negative 14 times 2 plus b. Negative 12, just plugging in the y value and the x value from the point and the tangent line that we found. This is going to be negative 28 plus b. We'll add 28 to both sides. And I think we come out to be that b, if I've done my math correctly, should be 16. So, what does that tell us? Well, if we go back to our tangent line, well, 16 doesn't work. Negative 12, plus 28. I got 16. Oh, apologies. Hopefully you guys saw that error before I did. This should be negative 2, so this should be positive 28. Which means that we should be subtracting 28. So 12 minus an additional 28, I think that's 40. I think we get b is negative 40. This is another good way to kind of check yourself. Minus 40. It's one of those days, isn't it? This is your sign to use a calculator. Final answer, negative 30. Negative 20? Man, I am not doing something right. I will be right back. Alright, hopefully you guys didn't make the same mistake I did. I actually plugged in both of these things wrong the first time that I did it, so I apologize. This is just another sign. You need to take these things going slowly. Regardless, if you plug in the right numbers of f of a is positive 12 and x is negative 2, plug those two things in, you get b is negative 16. And what I wanted to show you is, if you write the equation of the line y equals negative 14x minus 16, notice now the green line is perfectly through this red line. And notice, as I start to zoom in, right at the point negative 2, 12, notice the red and the green lines, what we would call the original curve in red, and the tangent line in green, notice that they are exactly the same. Now, they're not exactly the same everywhere. I mean, just looking at them like this, clearly, these are not the same lines. And so that's a really important idea that I just want to write down, and I want to make sure that we're all aware of it. Tangent lines approximate curves around the point of tangency. That's an important prospect of these tangent lines, is that they're approximately these curves. So, I can say something like, you come over here and let me change up my color, f of x is 4x squared plus 2x, which is approximately negative 14x minus 16 if x is close to negative 2. Now, how close is close enough? There are other calculus classes that will talk about how close it is. But as just sort of an explanation or a more physical example, what is f of negative 2.1? Now, this one, I don't trust myself for. I am going to use a calculator. And I should be using a calculator for all of these. And a lot of these mistakes that I'm making go away if you'll use calculators. But for f of negative 2.1, I get an exact value of 13.44, which is approximately equal to just plugging in negative 2.1 here, which is going to be negative 14 times negative 2.1 minus 16, which is 13.4. So the actual function is telling me 13.44, whereas the tangent line approximation is telling me 13.4. That's close between this number and this number. Now, if I was trying to compare like f of 9, which is much, much further away, so if you think about it, f of 9 is what? 6. Sorry, it's 342. Is not close to plugging in negative 14 times 9 minus 16. I get negative 142 using the line. So again, going back, tangent lines approximate curve around the point of tangency. And sometimes this is called a neighborhood. other calculus classes that will talk about those. So, how do we find the derivative? Well, as long as we have a function and a point on the curve, we can use either definition, but I will say I prefer this definition a little bit more. It goes real nicely into what we're doing. We found this term and this term separately. And reminder, this always is going to happen where the constant term goes away. And if it doesn't go away, that means you either have some more math to do to make it go away, or it means possibly that you've made a mistake. Okay. I want to look at a real quick other one. So, once again, we have a function. Now, this is a function of t values. And I want to point out, t values are... they're just changing t's for x's. But I want to point, we're only told a. So what is f of a? Well, as a reminder, you're just going to plug in. So f of a is f of negative 1, which is going to be 4 times negative 1 squared minus 2 times negative 1. This is 4 times 1 minus 2, or plus 2, which is going to be 4 plus 2, which is 6. Now, I am expecting that when I plug out f of a plus h, I should get a 6 floating around. Let's see if that happens. So once again, it's going to be 4 times the term negative 1 plus h squared minus 2 times negative 1 plus h. And as a reminder, a plus b squared can be written as a squared plus 2ab plus b squared. Maybe that helps. So I can rewrite this as 4 times negative 1 squared is positive 1. 2 times negative 1 times h is going to be negative 2h plus h squared. Or if you would rather write them, FOIL them out, that's also a way to do it. This one, though, we just distribute. This is going to be plus 2 minus 2h. Now we're ready to distribute out this 4. We'll say it's 4 minus 8h plus 4h squared plus 2 minus 2h. We have some combinations. There's our 6. We were expecting that. Negative 8h minus 2h. It's going to give us negative 10h. And we have a 4h squared that sticks around. Okay. So, it does stick around, which is fine. But the important thing is we have our f of negative 1 term. We have our f of negative 1 plus h. We're now ready to write the derivative. So once again, the slope of the tangent line is the limit as h approaches 0 of this term, 6 minus 10h plus 4h squared, minus this term, minus 6 divided by h. And, once again, notice the constant term cancel, and this always happens. So we're left with the limit as h approaches 0 of negative 10h plus 4h squared over h. Now, in the last one, I just kind of canceled both of these h's. Something slightly differently I want to do is I'm going to rewrite this real quick just to kind of prove that I can do this. If you pull out an h from both of the top and an h from the bottom, essentially we're factoring it, we are allowed to cancel because h does not equal 0. And once we've done that, something is continuous because it's a polynomial. So we just plug in negative 10 plus 4 times 0. The slope of the tangent line is negative 10 at x equals negative 1. And another way to write this, the slope of the tangent line, is we sometimes write f prime. That's what we call this little notation right here. We call that apostrophe. We call it the prime notation, which says we started off with a function f, but now we've done something to it, we've derived something from it, we now call it f prime. And that's the same thing. It means the slope of the tangent line. But one nicer thing is that this presentation also tells you a. So that's just a slightly nicer presentation. It's something that you're going to see quite a bit is this prime notation. There's a couple more derivative notations. We'll talk about those as we get to them. Okay, we're going to jump to a slightly harder type of function to do this limiting process on. And it's going to be a rational function. It's a certain kind of rational function. And it's not difficult. It's more difficult than the previous, but we have also, hopefully really practiced this. So let's try this example. F of t is 1 over 6t plus 1 at a equals negative 2. So as a reminder, we want to calculate f of negative 2 as well as f of negative 2 plus h. So this is going to be 1 over 6 times negative 2 plus 1, which is going to be 1 over negative 12 plus 1, which I think is 1 over negative 11. There's my f of a. Now, this one, slightly harder, but hopefully something we can still accomplish. 1 over 6 times negative 2 plus h plus 1. Don't forget the plus 1. Now, if we move this out, we're going to get negative 12. We can just distribute. Plus 6h plus 1, or 1 over negative 11 plus h. Now, as long as we follow the rules, we will be able to define this limit, but I want you to be very careful on how we combine these terms. And specifically, I want to remind us that we want to add, we want to find, I don't want to add, I want to find common denominators. And that's going to be my biggest hint there. So once again, f prime of negative 2 is going to be, the limit as h approaches 0 of, and by the way, this is also the slope of the tangent line. Going back up here, f of negative 2 plus h minus f of negative 2 divided by h. Okay, keeping the limit. This is going to be 1 over negative 11 plus h minus 1 over negative 11, all divided by h. Okay, a couple things that we're going to do to make this a little bit easier. I'm going to pull out this negative sign. I'm going to put it right here. Okay, so subtracting negative 1 over 11 is the same thing as adding 1 over 11. Now, how do we add something like 1/2 plus 1/3? Well, we're going to multiply by the number 1 on each side. We're going to rewrite it as 3/6 plus 2/6 is 5/6. So, how are we going to get those like terms? Well, this one I'm going to multiply by the other denominator, 11 over 11. And this one, the rightmost one, I'm going to multiply by this denominator, which is negative 11 plus h, over negative 11 plus h. Okay? So, what does that leave me with? The limit as h approaches 0 of 11 over 11 times negative 11 plus h plus negative 11 plus h over 11 times negative 11 plus h, all divided by h. Maybe I should extend that down. Notice, same denominator. I can actually directly add these two things together. So this is the limit as h approaches 0 of 11 minus 11 plus h divided by 11 times negative 11 plus h, divided by h. And maybe I'll just choose to make this one a little bit bigger so we remember that this fraction is being divided by h. Notice the 11 minus 11 cancel, and this is the limit as h approaches 0 of h divided by 11 times negative 11 plus h, all of that divided by an additional h. And I can divide in the same way that I've done all the other times. Notice our constants cancel, leaving me an h to cancel with the bottom. Now I have something that is, for this value, continuous, and I can just plug in. And I get 1 over 11 times negative 11 plus 0, or 1 over 11 times negative 11, negative 1 over 121. All right. Apologies, I just got an email coming in. Now, once again, that is the slope of the tangent line. All right, I want to talk about one more problem, and this is going to be more conceptual, and we're going to talk about how we can use derivatives in the real world. So suppose the speed of a car is given by v of t, where the v stands for velocity, is t minus 10 squared on the interval 0 to 10. So notice this notation implies that 0 is less than or equal to t is less than or equal to 10. So, and I assume t is measured in seconds. And by the way, this is a car that is stopping. So if we do v of 0, we're going to get 0 minus 10 squared, which is just negative 10 squared. It has a speed of 100. And maybe that's meters per second. But after, let's say, 5 seconds, because we're slowing down, we've slowed down to 25 meters per second. So the idea is that we're going to slow down, it's going to stop. At any time value, I can tell you what. Now notice that v is the velocity. It is itself a speed. It is a rate of change. Okay? So, what would it mean to be the derivative, is my question. Well, how does it change? So, the important relationship that I want to talk about is distance as we go down, velocity, and acceleration. They all have the relationship of derivatives. Specifically, velocity is the derivative of distance, and acceleration is the derivative of velocity. Velocity is well, and let's talk about some units. Distance, let's say it's measured in meters. Well then, meters per second. Acceleration is meters per second, which usually we write as meters per second squared. Now, if we change meters to miles and we change time to hours, we're still technically right. You could also talk about distance in miles. That's distance. Velocity would then be in miles per hour. And then we can talk about your acceleration as miles per hour squared. And we can choose any of these units that we want. Okay? So, the typical way it goes is we might use S for distance, and let me write this right here. We might use V for velocity and A for acceleration. S prime of t, the derivative of position, is velocity. V prime of t is a. And we'll talk about this more as we get to this section. You could also talk about the second derivative, the derivative of the derivative. One derivative takes you from speed to velocity, from distance to velocity. The second takes you from velocity to acceleration. Okay, so distance, velocity, acceleration. You're going to see a lot of this type of structure as our function is measured in some unit. The velocity is unit per time, and the acceleration is unit per time squared. That's going to be a real common solution. So hopefully this video was useful. Practice whatever you need on the homework, and I wish you all a wonderful rest of your day.